Um, Thanks to the organizers for organizing such a great workshop. I've really enjoyed the talk so far. I'm Bloem-Reddy, and I'm from Colombia. This is work with Peter Orband. So the starting point of the talk is recognizing sort of a collection of things that, as a community, we've sort of settled on as arising in a typical network data set. So things like heavy-tailed degree distributions or power laws, things like chains or pendants or hubs, other things like triangles or self-similarity, and the list goes on. I put sparsity in quotes after the discussion yesterday. We use it as maybe a conceptual tool for our models. But the point is that all of these things arise from some sort of complex dependence in our data set. And so we would like our statistical models to be able to accurately capture that dependence no matter what sort of task we're doing, whether it's estimation or testing or something like that. So as a collection of Bayesians, or mostly Bayesians in the room, oftentimes the starting point is exchangeability of some form. So we've heard about that in sort of a number of ways it can enter a model with networks. And for me, one of the sort of key implications of assuming exchangeability is that it gives you some sort of nice conditional independence. So in the Aldous Hoover representation, so this is exchangeable vertex models, basically it tells you all of your edges are conditionally independent. And that's nice for a number of reasons. It lets us take this big, complicated dependent structure and just break it apart into edges, so the thing just sort of falls apart for us. We can put all of the dependent structure in the parameter, so the graphon in this case. Could be a random measure or something like that. And then it lets us use simple observation distributions for actually realizing the data. So this allows us to have efficient sort of tractable inference. It informs proper model criticism and testing. So all this is to say that conditional independence is really, really useful. On the flip side of that is that if we assume too much conditional independence, we can really constrain our models. So if we are in the case where we only have one observed network data set, then assuming fully conditionally independent edges says that the actual realized value of this edge doesn't depend directly on realized values of the other edges in that particular data set. Okay, so increasingly strong dependence in these data sets, when we try to model them sort of quasi-independently, makes our parameter spaces get really, really complex and really big quickly. So too much conditional independence can restrict our models. So using this as sort of a jumping off point, we might think about how to specify a model where we're not assuming explicitly any conditional independent structure, and we want our model to sort of infer that along the way. Okay, and still we would obviously like to be able to fit our models and perform inference and that sort of thing. So we don't want to trade too much. We don't want to lose too much tractability and interpretability and that sort of thing. So a really simple model that tries to do this is so we'll add edges one at a time, and the natural interpretation is as a dynamic model. But I would like to stress that this really is building up a dependent structure one edge at a time. Okay, and so the way we do it is we start with some graph with t edges, and at the next step we're going to insert an edge. So the way we do that is we randomly choose a vertex in the existing graph, and I'll talk more in a second about what some sensible choices for that random choice looks like. And then we flip a coin, and if it comes up heads, we just attach a new vertex with an edge to that existing vertex. If it comes up tails, then we're going to do something a little more complicated. We're going to insert an edge between two existing vertices. And the way we do that is we start on that randomly chosen vertex, and we perform a simple random walk of random length. So we draw a Poisson random variable, and we walk for k plus 1 edges, or steps, sorry, and then we insert an edge between the start and the end of that random walk. Okay, so this, in this form, it's a model for multigraphs, possibly with loops. If you want to make it appropriate for simple graphs, binary graphs, you can think of any number of ways to modify the rule. So one simple way that I'll talk about here is just if you have a random walk that either ends where it started or ends where there's already an edge, then we just attach a new vertex to the starting point. Okay, and this is really just sort of a modeling choice, and in this case, it's a simple thing that you could change if you thought it was a bad idea. Okay, so before I talk about what this model sort of gives you, I want to build some intuition. So for a single random walk, so you fix your graph and you look at a random walk on that graph. So the lambda parameter, which is the mean parameter of that random walk length, in the sort of infinite limit, this gives you infinitely long random walks, and the stationary distribution of a simple random walk is just the degree distribution. So it ends on a vertex proportional to that vertex's degree. In the other limit, lambda going to 0. Remember, we're adding 1 to the Poisson variable, so this just looks at the neighbors of the starting point. Okay, so this is a purely neighborhood dependence as opposed to a sort of global dependence that doesn't care about how the edges are arranged in the graph. It just cares about the degrees of the vertices. So that's the sort of random walk interpretation, and you can also look at from a regularization point of view. This regularizes the length scale of dependence between edges in the network. If you look at you start at a vertex u, and you want to calculate the probability that it ends on some other vertex, and you marginalize out the length of the random walk, you get this nice closed form expression that's a function of this matrix exponential here, where this is the normalized graph Laplacian, and which is closely connected with diffusions on the graph, and known as the heat kernel or diffusion kernel. And so lambda basically damps the spectrum of L depending on what it is. So in the infinite limit, this is you're only gonna get the smoothest eigenfunction. Is the degree matrix, so it's a diagonal matrix of degrees in the graph. Okay. So just some pictures of what you can generate with different parameters of the model. So I said before, in that first step, you want to choose a vertex to sample to attach the new edge to, and the sort of most basic distribution is the uniform distribution over vertices. And so if you do that for varying parameter settings, so in the middle row here, I'm increasing alpha, so the rate at which new vertices are attached, and holding lambda fixed, and then diagonally holding alpha fixed and increasing lambda. So for increasingly long random walks, these branches start getting pulled back in. You get edges created across sort of different parts of the graph, and then you see more tree-like structures. This is for the binary simple graph case, and so for very small values of lambda, it's actually creating a lot of vertices as well. The other sort of canonical distribution on vertices is the size biased or degree biased distribution. And so in this case, you get a very strong preferential attachment type behavior, and so you see the emergence of hubs sort of throughout the graph. Okay. So hopefully this is somewhat convincing that you can generate a lot of interesting structures just with two simple parameters and a distribution on vertices at each step. And we'd like to be able to say something concrete about these things. So one thing that, if if you come up with a model these days, you're sort of expected to show some sort of heavy-tailed degree behavior. And in the sort of the preferential attachment case with an infinite length random walk, it's pretty easy to show that you just get, in the case where for multigraphs, you're sampling the initial vertex from the degree bias distribution, then you get a nice heavy-tailed degree distribution. Okay, for finite lambda, this is a little bit trickier to treat analytically. Simulations sort of show, so the orange line here is the preferential attachment version, and finite values of lambda sort of behave the same way. Okay, so we have a nice heavy-tailed degree distribution. So this is, of course, the probability that a randomly sampled vertex gives you a degree d. Okay, these also, the order in which the vertices come into the graph has some information. And so if you look at the degree sequence, so you keep the vertices in the order in which they enter, this converges to a random limit, and it has this nice stick-breaking construction. So I won't dwell too much here, but it's sort of interesting in its own right as a probabilistic object. Okay, so hopefully, you know, the argument here is that the simple model with two parameters generates a lot of structures that you see in real network data, and so then of course it's only really useful as a statistical model if we can do inference. And in the sort of easy case, you observe the order in which the edges come in. So it's a sequence of edges. And in that case, the likelihood just factorizes across that sequence, and you can do maximum likelihood, or you can do simple Bayesian estimation and inference. But that's typically not the case, that we actually see these edges. So the case that I spent a lot of time on is trying to figure out how to do inference in the case where we observe one graph, and we want to really sample over this latent trajectory. And by trajectory, I mean the order in which the edges impose themselves in the dependent structure of the network. Okay, the sequential nature of the model is sort of a natural fit for a sequential inference algorithm, and so we formulate a particle Gibbs sampler where we alternate between sampling a latent trajectory and then condition on that trajectory. And then we're basically in this easy case, and we can do Gibbs updates to the parameters. Okay, it's tractable. I will say it doesn't scale well as you might expect because of this very high dimension of the space. So maybe at the end I'll say a few words about that. But I was told by a friend that in these talks nobody cares about your inference algorithm, so you just, at least about the details of it. So you just, I won't dwell on it too much, but just to convince you that it does something sensible, this is with synthetic data, showing that we can recover the parameters. So for each combination of parameters, alpha and lambda, I've generated a graph with 400 edges, and then forgot that I generated it myself, just looked at the one graph. And then I tried to see if I could recover the parameters. And you see for the black dotted lines are the true values of the parameters, and the contours are the posterior densities. So it does a pretty good job across sort of a big part of the parameter space. I will point out that this little corner here, actually this whole column with short lambda means that lambda and alpha are sort of interfering with each other. This was the rule that said if we had a random walk that ended where it started or ended where there's already an edge, then we're going to create a new vertex. And so these two rules, or that rule sort of mixes these parameters up. So maybe indicates that more careful thinking about that type of rule would be necessary. Okay, so fitting to real data, we have two two real networks. This is the protein-protein interactome that has popped up in a number of talks this week. And then something topologically very different. It's the largest connected component of a NIPS co-authorship data set. So this looks like a chain with, you know, some really locally connected communities. And so the posterior density for the two random walk types of models actually really captures that well. So if you look at lambda, the posterior density concentrates between 1 and 3, and that's, you know, if you had to guess, that's probably what you would guess for that for the NIPS data set, right? So you have these very local dependent structures. On the other hand, with the protein network, you have sort of a mix of scales, and you have some very local scales and some more highly connected parts of the graph, and the posterior sampled values of lambda sort of mix between the two. So it also suggests that maybe a mixture model over lambda for modeling purposes might be better for this data set. Okay, so in addition to sampling the parameters, you can also use the sort of implied ordering on the vertices to do interesting things, like look at the centrality of the vertex. So this table is full of ranks of different statistics in the network, and the colors correspond obviously to these rows in the table. And by sampling order, I mean in the particle Gibbs sampler, I'm sampling over the posterior distribution of these latent sequences, and so the earlier a vertex arrives in that sequence on average, the higher it is in the sampling order. So these two red dots, the right and the left, have the same median sampling order, and so by this measure of centrality, they're tied. And if we compare this with other notions of vertex centrality in networks, we see that it's capturing something more than just degree. So this first ranked vertex is the 14th ranked vertex by degree. So that's this one here. It only has 4 edges, I think. But it's very high in things like between the centrality, which is the number of shortest paths that go through the vertex, and it's the top in information centrality, which is a notion of the amount of information being sent and received from that vertex to the rest of the network.
These are posterior modes or something? What are these? What are the numbers?
Here, these are the ranked of the median sampling order. So this first one, its median sampling order was 6, and that was
That's the median sampling.
Yeah,
Okay.
yeah. But so it's the rank. Yeah. And again, these are the ranks of the degree, and not the degree itself.
That's the posterior median of the degree.
So these are just statistics. They're not sampled. So the degree of this vertex is 4, and if I rank in descending order the degrees of the vertices in the network.
The actual data.
Yeah, of the actual data. Yeah. Okay. So then, as sort of another question that you want to ask about your model is, does it fit the data? And Peter Hoff had some nice posterior predictive checks in his talk, and we've taken a similar approach here. So I'm comparing the two random walk models with, as just a baseline, the Erdős-Rényi model, and then the infinite relational model, which is the Bayesian non-parametric version of the stochastic block model. And in experiments, actually, this tends to do quite well because it can basically throw as many parameters as it wants at the data. Okay, so here I'm looking at, I fit the model, and now simulated 1,000 networks from those parameters, and this is the degree distribution that I've put it on a log scale. So the black line is the real data. This is for the protein network. So we see the sort of well-known Poisson behavior of the Erdős-Rényi model, not doing well with the real data. And so the size biased version of the random walk model seems to create too many hubs. But with a couple parameters here, we seem to be capturing quite a bit of this behavior. So the degree distribution isn't very focused on local structure. So something like the edgewise shared partners. So this is introduced a while back, and it's really just, so if you look at two neighbors in the graph and you look at the number of triangles that they participate in together. So this is a distribution over integers again, and you see that these models capture that behavior quite well. And then finally, we look at the pairwise geodesic distribution. So this is pairwise vertex looking at their shortest paths together. And so this again captures something of a local structure that emerges from all of these interactions. And again, you see, so in the size bias version, these too many hubs are really sort of destroying these shortest paths. But we see that the uniform random walk model does pretty well. I will note the infinite relational model doesn't guarantee that you have a fully connected graph, and so you have a number of isolated vertices that put a spike on infinite length geodesic. But I'm not too worried about that. It's just sort of an artifact of the model. Okay, so all of these things tell us something, but it's not totally clear what they tell us, and that's a large part, in fact, due to the fact that we still don't, it's a bit ad hoc to say, okay, I'm going to have this set of statistics that I think describe my graph well, and so this is what I'm interested in capturing. I think as a field we've inherited these statistics from network science and from sociology and the applied fields, which is a good thing on the one hand, but on the other hand, sort of indicates our lack of understanding of what makes a network a network. So we look at these pictures, the IRM did pretty well in these posterior predictive checks, but if we look at this resampled picture of it, it's missing quite a bit of the interesting structure in the real data. Obviously the Erdős-Rényi, I think everyone knows is a bad model, but just for comparison. And then the random walk models obviously aren't perfect, but they seem to be doing a pretty good job of capturing some of these really dependent structures like dependence in the chains and that sort of thing. So you know, there seems to be parts of the real data that would fit well with this, and parts that fit well with this, and so maybe, you know, a mixture over the two would be a good modeling choice in the future. So with that, I will wrap up. So we've constructed a class of models that don't impose a certain conditional independent structure on the model, and we just assume that there's a flexible dependent structure, and we want to infer that. So the model as a generative model gives an interesting range of structures with just a few interpretable parameters, and then it does admit tractable analysis and inference algorithms. That being said, you do pay quite a bit of a price with not assuming this full conditional independence. So I have a burning question that I'm working on, that I'm thinking a lot about, is there a balance between saying, okay, we don't want to assume anything about the conditional independent structure, and we also don't want to assume that it just fully decomposes. Is there something in between where we still get some nice inference, but sort of more faithful models that are more faithful to the data? The second sort of question that has come up over and over again in working with this model is that when you try to compare to a different model that makes very different assumptions about the data, you're really limited in how you can compare them. So in the machine learning literature, link prediction is a very common sort of metric of model fitness, but that assumes that your edges are conditionally independent. So you can't do that properly with a random walk type of model. So I'm thinking a lot about how to do this in a principled way. The paper will be on archive soon. Yeah, it'll be on archive soon. Unclear quite when, but soon. Okay, thanks.
With the NIPS data set where you
Yep.
had that linear structure,
Yeah.
is there any interesting interpretation of what that axis is?
That's a good question. I don't know. So this community, I mean, the NIPS data set comes with the names of the people. This community happens to be mostly sort of the Israeli machine learning community, and then there's some associated people. I think EY is this node here. But yeah, so to answer your question, I'm not sure. But yeah.
So for your last question about comparing networks in a principled way, you have to think about what you mean by principle. If you mean that you want to look at small subgraph counts, then I can give you a talk after lunch.
So I understand that.
To do that.
There
are metrics and network comparison.
Yeah, but if you decide that subgraph counts are appropriate for your data, then you're assuming some structure about your data. So subgraph counts are the sufficient statistics of these vertex exchangeable models. So
No, but you don't necessarily have to assume that they are sufficient statistics. But so what I'm trying to say when you say you compare networks in a principled way, you might come up with very different results depending on whether you want to compare local structure or global structure.
I agree completely. Yeah. So by principled, yeah, I should maybe put principled in quotes. It really depends on what you're looking for. I agree.
So I don't think there's a single answer.
That's probably true. Yeah. Okay.
Yeah, can I, just on the same general point on your last question, last burning question, I mean, it sort of begs, for me, it sort of begs the more fundamental question of why? And why do you want to build these models? What are you going to use them for?
Yeah.
There are various possible ways to think about how to frame the conversation there, but let me hear your thoughts on that.
So I will give you the most general version in my mind, which is if you want to do any sort of statistical inference with network structured data, you want your estimation and your inference to take account of its dependence, otherwise you can't trust your conclusions, right?
Going down one level, so inference on what?
So let's say you wanted to, well, okay, if you condition on an observed network, then you don't have to really worry about this sort of thing as much, right? But if you're interested in performing some sort of inference over the network structure itself, then you do need to take account of these intricate dependencies.
So why do you want to model a protein network?
It's a good question. I would say if you're interested in let's say directing more experiments on looking for different types of interactions, then you want to understand this. I think evolutionary biologists are also interested in how these proteins interact, and of course they don't. The network isn't changing on a time scale that necessarily we can observe, but I think they are interested in how these things have evolved over time.
Well, I'm assuming maybe you're not so interested in modeling the protein networks, but whoever is, their inference, what they want to get out of it would be what determines what makes the method principled, right? So I mean, I imagine that would be what you meant by that. But I had a question on the power law, the first, what was it, the 9th slide? You showed that it has a power law in when lambda is infinite, right?
Yeah.
And that it looks similar for finite.
Yeah.
Do you have a conjecture of what's going on there?
Yeah. So I mean, when you do the analysis, there's a tricky term that emerges, which is basically the probability of a self loop being created, because that increases the degree count by 2. And so in the infinite limit, you can just, where you started doesn't matter, right? For just based on simulations, if the probability of a random walk ending where it started, if that goes to 0 faster than the number of edges that are inserted, then you get this exactly. So that's really the only thing that makes it a little tricky.